Hey guys, welcome to Electricity Part 2. Here we are going to take a look at static electricity, electric circuits, electric quantities, electric components, and hazards. So let's get started. So, charge and static electricity. Objects are positively, negatively, or have a neutral charge. Generally, objects do have a neutral charge, but when you rub them over with a different object, you get a positive or a negative charge because electrons are being transferred from one object to another. The positive and negative charge have a similar phenomenon as magnetism, and its charge is measured in coulombs, and its SI unit is C, the one which you will use. Suppose say 5 coulombs, you will write 5C to ensure you get full marks because the units are very important when uh, when you're writing answers in an IGCSE exams. So you can create a charge by rubbing a cloth on a plastic rod. The electrons are transferred from one object to another, like I said earlier. So this charge made by rubbing a cloth on a plastic rod, I'll show you on the next slide. Over here you can see that electrons are lost from the dry cloth because they are rubbed off. Suppose there's 5 electrons on a dry cloth and 5 electrons on a plastic rod and 5 there's a 5 plus 5 charge and a 5 positive charge here, and the 2 electrons are transferred from this dry cloth to the plastic rod, then that would mean that net charge is minus 2, so it's much more negative now. So the electrons are gained here, but now we are left with a plus 3 charge on the dry cloth because the charges are not equal, so now the dry cloth is positively charged. Over here you can see a similar phenomenon, except the electrons are gained by the cloth and not the rod. Electric fields. Similar to magnetic fields, charges also have an electric field. So there's a positive charge which has an electric field and a negative charge which has an electric field. This electric field is the region in which the charge experiences a force. So if you bring a negative charge in the electric field of a positive charge, they will attract each other. It always goes away from the positive charge and into the negative charge. That's how any electric field works. A positive or negative charge depends on the electrons present on the surface. This is a key point in static electricity. You can use any kind of insulator like metal, any kind of insulator like plastic or cloth. It does not matter because the electrons are not going through the plastic. It is not conducting that electricity. It is just on the surface, and this is static. This is static electricity. It's not moving anywhere, and it is always related to another object. So here you can see the charge going away from the positive and into the negative. It is again a similar phenomenon to magnetism, like when the magnetic field lines go from north pole into the south pole. You'll need to watch the first part of the video to understand what I'm saying here. So conduction and insulation. Metals conduct electricity with the exception of the non-metal graphite. So how they conduct electricity, I explained before. They have free electrons. It's a lattice of positive ions in a sea of electrons. That's the metallic bonding. That's how metals work. And these free electrons, this sea of free electrons, they can move through the metal. They are not static. That's why they can conduct electricity. And graphite can conduct electricity because there's thin layers of graphite. It's a 2D shape, so the electrons can easily pass from one part to another. So like I said before, insulators prevent electrons from passing through, like plastic and glass, but they can have a charge because it is static. It is just on the surface. It's not going through the substance. Charging by induction. Bringing two charged objects close together but not touching them creates a gradient of sorts. There's a charge gradient created because if you bring a positively charged sphere next to a negatively or a neutral charged sphere, the negative charges from the neutral sphere go towards the side in which the positive charge is brought together, and the positive charge is repelled. So you have a gradient. There's a negative on this side and positive on this side. And then you use an earthing wire so that the electrons are dissipated, creating a net positive charge. So what I'm basically saying here is that if you bring an earthing wire to the negative point, the electrons are all going through the path of the least resistance from the earthing wire into the ground, and so there's only positive charges left. So that's how you can create a charge on an object without touching them, without bringing them close. Here you can see what I just said. They just used A as a different kind of earthing and they separated them. This is how you charge by induction. And this is also charging by induction where you use some kind of earthing. Here this person used his finger, but which is very dangerous when you are talking about large voltages or there's a lot of current flowing through it. So I'd advise you not to do this. Yeah, you can use a earthing wire. It is much more safer that way. So current, voltage and resistance. Current is the rate of flow of charge shown by the equation Q is equal to I into T, and its units are amperes. You rearrange this equation to get rate of flow of charge, which is Q divided by T. Whenever I say anything about rate, it always means that uh, anything is being the rate of x, that means that x is being divided by time. So the x is happening in a period of time, so that's the logic you need to use. Voltage is either EMF, which is electromotive force, the potential difference of a power source, which means that the potential difference in a battery or a cell, which is the energy per coulomb. This is an equation that you need to use, which is V is equal to E upon Q, which is energy per coulomb. Q you use as a symbol for equations. That's what you need to use. I for current, Q for coulombs, and V for volts. Potential difference is the amount of energy transferred between 2 points, and resistance is opposition to unit the currents, and its units are ohms. So we have covered 3 units here. Current has the unit amperes, which is measured with an ammeter. Voltage has the unit volts, and the resistance has the unit ohms. So here we have a simplified diagram. The voltage or the EMF of a cell, it pushes the current around the circuit, but resistance opposes this change. The resistance opposes this current by preventing it from going through. There's two types of currents. There's a conventional flow of current that we regularly use from positive to negative, but this actually is uh, incorrect. The actual correct flow is electron flow, which is from negative to positive, not positive to negative terminal. It goes from negative to positive terminal. But in your final exams, in your IGCSE exams, you need to use the conventional flow because that's how many electric circuits are built. We do not use electron flow, even though it is correct. Resistance of wire. The resistance is the opposition to current. A long wire will offer more resistance as current has to travel more distance, and a wire with a small cross-sectional area offers more resistance as current moves with more difficulty. You can imagine this as a car traveling on a highway or on a road. A long road, which means that a car has to burn more fuel, it has to travel much more distance than a short road. Or when I'm talking about cross-sectional area, you could imagine that as traffic. There's a crazy traffic jam, and the car cannot move really quickly. It has to move very slowly. So that means that it has to move with much more difficulty. That's the logic you could use to remember the resistance of a long wire or a wire with a small cross-sectional area. Here you can use this phenomenon. So you remember this, that resistance is always proportional to the length, but the cross-sectional area is inversely proportional to resistance. So if you double the cross-sectional area, it will halve the resistance because there is more space for the current to go through. I hope that makes sense, because you can imagine that as a much more wide road, so there's no traffic jam now. Electric graphs and Ohm's law. Ohm's law states that V is equal to I into R, which means that resistance is inversely proportional to current and directly proportional to voltage. This is a graph for an ohmic resistor. It means that it is obeying the Ohm's law, and that it will continue obeying the Ohm's law. But here we have a non-ohmic resistor. A non-ohmic resistor, an example of it would be a lamp. A lamp is a type of a non-ohmic resistor because the filament in it acts as some kind of a resistor. When the current is flowing through, it heats up. So there, the resistance starts increasing rapidly from from a very small point, and it is not proportional. It's a rapid increase. It's kind of like a logarithmic graph. So you need to remember how the ohmic and non-ohmic resistor behaves. Electric energy and power. An important formula that you need to memorize is E is equal to IVT, and its units are in joules. It states that electric energy is current multiplied by voltage in a period of time, or power in a period of time, or, as remember what I said before, energy can also be demonstrated as Q into V by rearranging the equation V is equal to E upon Q. So it is also charge into voltage. So the three definitions for energy would be: energy is current into voltage into time, or charge into voltage, or power into time. Another formula is power is equal to I times V. For power of any electric appliance, its units are in watts. So P is equal to IV and E is equal to IVT. These are the formulas that you need to remember, and then you need to plug in other different formulas that you have learned, like V is equal to IR, or V is equal to E upon Q, or Q is equal to IT, and you need to connect all of these together. You need to have that kind of logic for a complicated IGCSE question, because sometimes the questions come for like 5-6 marks where you have to use all of that logic together. So don't get scared. It's just basic maths. You just need to plug in these equations and connect them to each other. Transmission. Electricity from transformer is transported using high voltage to minimize power losses or energy losses. Because the same amount of energy is to be transferred using a larger voltage, less current is required, which minimizes the resistance, causing less heating of power lines. Now this might sound confusing, but I think some basic mathematics would help. So we write 6 is equal to 2 into 3, but we can also write 6 is equal to 3 into 2. Imagine now that 6 is the 6 joules, and first we take the example of 2 into 3. If there's 2 volts, okay, and then there's 3 amperes. If there's 2 volts and 3 amperes, you're still going to get 6 joules. But what if you use 3 volts and 2 amperes? That would mean that there is less current flowing through, which means that there is less resistance, which would mean that the power line is not heating up very much. That would mean that there is a less chance of a fire or a burning hazard or a shock hazard. So you need to transfer electricity at very high voltages. I just gave you a small number, but the actual amount is much higher than you think. So you need to stay away from power lines or any transmission lines, because those are very dangerous. You could get shocked and get killed instantly. Here are power lines, and there's ridiculously high voltage flowing through them. So electric circuits. There are some electric circuit symbols and some diagrams you need for IGCSE physics. You can find them on the back of your textbook. The textbook is in the description. The diode keeps the current flowing in one direction, so it prevents the alternating current. When you use alternating current, you need to transfer it to DC. So for example, if you have AC coming from a transformer and you need it for a DC operating uh, appliance, like maybe a fridge, you need to convert the AC to DC so that it does not damage the fridge. What you do is you put a diode so that when the current is alternating, when it moves from point A to point B and back to point A, it will stop the movement from B to A, and it will keep moving it from A to B. So there's this lapse created by getting a diode. Variable resistors alters the resistance and therefore current in a wire, and it is used in fan regulators. So what I mean here is that when you want to increase your fan speed, when you want to make it much more cooler, what you do is you change the regulator to a point where there is very low resistance. The variable resistor gives very little resistance and more current can flow through it, which can make the motor turn much faster, giving the fan a greater speed. Alternatively, when you decrease the fan speed, you make sure that the resistance is very high by turning the variable resistor or the regulator, which we see, so that the current flowing through is very less, and so the fan does not move with as much speed. And LDR and thermistors are used for environmental changes to alter resistance, and then you can use this to alter the current flowing through, and then you can use that for many other things, for security purposes, or for say for keeping some animal in its habitat in a comfortable space. So you can use this to create an artificial it can depend on the environment. So let me show you an example here. So we have when there's very less light, you have a very high resistance. So like during the night time, if you have an LDR, which is the light dependent resistor, its resistance will be very high. So suppose if you want a switch to if you want something to work very slowly or work with less power during the night, or put it in a power saving mode, you make the light much less so that the resistance becomes very high and the current flowing through is very less. Similarly, for a thermistor, if you want to if you decrease the temperature and the resistance becomes high, or if you increase the temperature, the resistance becomes low. This is solely dependent on what kind of appliance you are using. And here are some diagrams for your IGCSE exams. When you're building a circuit diagram, you need to remember these components and how they look like. So here are some of the important ones: switches, cells, battery, diodes, resistors, variable resistors, light emitting diode, which is what you see in your LED lights. Those are just basically keeping the keeping the current going in one direction while also emitting light. And this is a lamp. You use this symbol for a lamp. This is a fuse, a voltmeter which measures the voltage, an ammeter which measures the amperes, a thermistor, and an LDR that I told you about before. So always remember that the voltmeter needs to always be connected in a parallel so that the voltage stays constant, and an ammeter is always in series because the current is always constant in series. More of that in the next slide. Over here you see voltage. It's in a series circuit, it adds up V1 plus V2 plus V3. So if you have a lot of cells connected together, a battery, you calculate it by E1 plus E2 plus E3, which gives you voltage, which is Vt. Over here in a series, the current is constant. The same current is moving through the series. So if suppose 2 amperes is moving through, it will be 2 amps in R1, it will be 2 amps in R2, and it will be 2 amps in R3. It is constant throughout the circuit. But the resistance is R1 plus R2 plus R3 in a series circuit. It adds up similar to the voltage because the resistance keeps increasing as you add more components in series. The voltage, however, is constant in a parallel circuit. That's why you use a voltmeter in a parallel circuit, and you connect a voltmeter in parallel so that the voltage stays constant in it. And you connect an ammeter in series because the current stays constant in it. And the current adds up in a parallel circuit because it splits up. So we have I1 plus I2 plus I3, and the resistance is 1 divided by R1 is equal to 1 divided by 1 divided by R2 is equal to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3, and then you get a reciprocal of 1 divided by RT to get RT, which is the total resistance of the circuit. So the features of a series circuit is that if one component burns, the current becomes inactive because the current is flowing through, and if there's a break in this circuit, it will stop flowing through. But an advantage of parallel circuit over the series circuit is that even if suppose this wire breaks down and R1 stops working, R2 and R3 can still continue going. So the current can still flow through these because the current splits up in a parallel circuit, but it stays the same in series circuit. Potential divider circuits. When resistors are connected in series and the voltage is shared between them, to find the voltage in a specific resistor, you use the equation V out is equal to V in times R1 divided by R1 plus R2, and moving a sliding contact upwards or downwards, which changes the potential difference of the resistor, which means that there is more or less resistance. If you move it upwards, there is higher resistance because a larger wire or a larger piece of wire is being covered, or a larger part is being resisted. But if you move it downwards, there is very less resistance because the current can easily flow through. So you need to remember that. This is how a potential divider circuit looks like, and this is what you use to calculate. This is actually labeled, you can use this, but this should be actually R1 and this should be R2 for the equation that we used earlier. This needs to be R1, this needs to be R2. You need to use that equation when it comes to potential divider circuits. You cannot use your regular this one. You cannot assume that V in is equal to V1 plus V2 plus V3 just because it's in parallel, because there's a resistance connected in series as well, so you need to take that into account. So this kind of questions can be really tricky, but much more easier when you get a hang of it. Relay circuits and diodes. Relay circuits remotely operate another circuit which may be inaccessible or very dangerous to operate. It uses the principle of electromagnetism in which the relay, which is itself an electromagnet, it induces some kind of force operating on a switch in another circuit, causing the current to flow. And like I said, diodes are used to rectify alternating current for DC devices, which is direct current devices. Here you can see how what I said. If it's moving in negative and a positive and a negative direction, the voltage is negative and positive in an AC. But what if you need only a positive current or a positive voltage? You use an AC, uh, you use an diode to correct the AC, so you only get a DC output. Excuse me. So binary and logic gates, using zeros and ones, we can operate any kind of machinery by the use of logic gates. Everything, all the computers, everything you see around you is just made of zeros and ones. It is the basic fundamentals because it is only answered by yes or no, or uh, binary, because there's only two possible combinations. The logic gates takes up commands and change it to some kind of a digital signal, and then a much more complicated connection of many logic gates perform a task. So suppose if you want to open up Instagram on your mobile, you click on it, but there's a crazy amount of logic gates which say that okay, now he has clicked on Instagram, which means that we need to use this gate in connection with this gate, and then you need to pass through so that there's one which is yes, uh, passing through the logic gate, and then you can open your app, and this happens within a fraction of a second or even smaller than that. You can demonstrate it with truth tables for logic gates, and this will be asked for you in the exams. These logic gates are not, and, nor, or, and NAND. These are all you need to remember, these five logic gates. And the truth tables for them are very simple. For NOR and NAND, you basically just combine NOT and NOT and OR functions. So here you can see in an AND gate you have point A and point B. So an AND gate will only allow 1 and 1, which is yes and yes from both signals from both points A and B, so that the output can only give 1. So AND gate is used for when you have like two car system and you need to operate both of them simultaneously at the same time, giving a yes for operation. A OR gate uses a 1, like, or 0, a 1 and 1, or a 0 and a 1. So it does not really matter if there's a 1 here or a 0 here, or a 1 and a 1 here, or a 0 and a 1 here. So what just matters is that you have 1 somewhere. That's why it's OR. It's either this or that. So that's how it works in a OR gate. The XOR and the XNOR gate, we do not require these for the exams. The NOT gate is basically the inverse function. So if there's zero input from point A, it would register it as a yes. If there's a no, it will register as a yes. If there's a yes from point A, it will register as a no in the output. A NAND gate is basically how it works. If there's a 1 and 1, as we saw in AND gate, it will actually give a 0 because there's a function of not here. If there's a 1 and a 0 which gives a 0, or a 0 and a 1 which gives a 0 in the AND gate, it will actually give the function of 1, because what it registers is that there's a AND gate and a NOT gate as well. So whatever function that gives a 0 or a no for an AND gate, which would mean an yes for a NOT gate. Similar function is for a NOR gate. You combine NOT and OR functions. So you need to remember this when they ask you in some logic gate diagram that what will be the correct sequence of inputs to get a final yes output to operate some kind of a machinery. Dangers of electricity. Common hazards of you need to remember are bare wires, damaged insulation, damp condition, and overheating. Damp conditions, so water conducts electricity. So if there's an open wire and there's a lot of water around it, you need to stay away, because even though you might not actually touch the wire, the electricity can still conduct through the water into your body. So that is very dangerous. Damaged insulation and overheating can easily cause a fire, and so can bare wires. So you need to remember that these are the common hazards. So to prevent a problem like a fire or a electrical shock, you use something called fuses and earthing wires. Fuses are designed to disconnect a circuit if it is overloaded and too dangerous. It is placed on a live wire with a circuit breaker. The fuse rating must be higher than the current in it or the appliance rating. So what I mean by this is that if there's like 5 ampere current flowing through a lamp, okay, and the lamp requires 5 amperes as well, okay, so the fuse will stay the same, and the fuse is suppose of say 7 amperes, but say a 10 ampere current flows through and the lamp has a risk of blowing up because the current is too high, and the fuse registers that. So when the current is flowing through, the fuse will break because it is much greater than actual rating of the fuse. So when the fuse breaks, the wire gets melted and the connection is stopped. That prevents the lamp from blowing up, and it is a much safer method. The fuses need to be replaced and the circuit breakers need to be replaced from the live wire if they blow up, because again, it is not just a surefire way of preventing it. You prevent it once, it's a one time shot. You can put it back again, but it does not work again and again with the same fuse. Earthing wire is also a safety measure to dissipate excess current or charge from a metal case to prevent electrocution. So this earthing wires used to prevent electrocution. It basically takes all the electrons from it and deposits into the ground, and so that you do not get shocked by touching it. It prevents electrocution. So these are some things that you need to know. And another part that's just a safety tip: if there's a fire because of electricity, you don't want to use water to combat that, because water actually conducts electricity. You should use sand for it. So this is another safety feature that you can use when it comes to dangers of electricity. You can see how it works. The current is passing through. This is the fault current from the live wire when you touch the electric equipment. But the earthing wire, there's no earthing wire in this. But if there was an earthing wire, it would prevent this current from going through the metal case and going through your body. This earthing wire deposits this fault current into the ground so that you do not get shocked. And this is how a melted fuse looks like. There's a circuit breaker inside this fuse, and if the current flowing through is very high, suppose if this was like a 10 ampere current flowing through, and then there's the 7 amp fuse and a 5 lamp uh, uh, 5 ampere lamp in the front, the 10 amperes is too high for the lamp, so the fuse melts the wire because it registers it as a higher current than it is. So what you always need to do is that the fuse rating must be just higher than the appliance that you're using. Suppose if you're using a 10 amperes appliance, the fuse rating should be suppose 12 or 13 amperes. It should not be so much so higher up that it will not even register the current flowing through, or it should not be lower than the appliance rating, or else the appliance will not light up at all and the wire will just get broken up because of the fuse. And that's all for your electricity part 2, and with this we have covered the entire chapter of electricity.